Have you ever stopped to wonder about the hidden genius behind the apps you use every single day? It's not really magic. It's actually a set of incredibly powerful, reusable solutions. So today, we're going to open up the programmer's secret toolbox and see exactly how they build our digital world. I mean, really think about that for a second. You tap in a destination, right? And boom, in less than a blink of an eye, your phone has sifted through this massive web of streets, traffic data, and countless possible routes to give you the single best path. How on earth is that even possible? Well, here's the secret. Programmers don't solve these gigantic problems from scratch every time. They don't have to. Instead, they rely on a well-stocked toolbox filled with proven, super optimized solutions for common problems. And two of the most important tools in this box are called algorithms and data structures. Okay, so an algorithm sounds kind of technical, but it's really just a fancy word for a recipe. Seriously. It's just a clear, step-by-step set of instructions to get something done. If you've ever followed a recipe to bake a cake, guess what? You've used an algorithm. In programming, it's the exact same idea, a precise plan to hit a specific goal. And if an algorithm is the recipe, then a data structure is your kitchen pantry and, how you've organized it. It's all about the way you store your ingredients, your data, so that your recipe can grab what it needs super efficiently. Are your spices alphabetized? Are all your baking goods on one shelf? The right organization just makes the whole recipe go a lot faster. So, first up, let's look at the tools for organizing data. The choice of how you store your information can have a massive, massive impact on how fast and efficient a program is. We're going to look at two really fundamental ways to do this. On one hand, you've got an array. The best way to think of this is like a perfectly organized shelf with numbered boxes. If you need box number 50, you just go straight to it. It's incredibly fast. But what if you want to squeeze a new box in between 25 and 26? That's a huge pain in the neck. Then, on the other hand, you have a linked list. This is way more like a scavenger hunt. Each item holds a little clue that points you to the very next one. So, finding the 50th item means you have to follow 49 clues first, which is obviously pretty slow. But adding a new clue right in the middle, that's super easy. And right there, that's the classic trade-off, speed of access versus flexibility. Next up in the toolbox, tools for creating order. Now that we have ways to store our data, let's look at one of the most common recipes programmers use, which is basically just creating order out of chaos. A huge part of programming is taking messy, jumbled data and sorting it. So let's check out the tools for that job. Now, the goal itself seems simple enough, right? Just take a jumbled list of numbers and arrange them from smallest to largest. But as you're about to see, the way you do this, the specific algorithm you choose from the toolbox, matters a lot. Let's start with a really basic tool. It's called Bubble Sort. It's pretty simple and intuitive. All you do is compare two items right next to each other, swap them if they're in the wrong order, and just keep repeating that. The largest values slowly bubble their way up to the end. It's easy to understand, and yeah, it gets the job done, eventually. The problem is, for a really big list, it is incredibly slow. Now let's look at a much smarter tool, Merge Sort. Instead of doing all those tiny little swaps, it takes a divide and conquer approach. First, it just splits the list in half, and then in half again, and again, and again, until it's just a big pile of single-item lists. And here's the really clever part. A list with only one item in it is, by definition, already sorted. So from there, it just intelligently merges those tiny sorted lists back together into one perfectly ordered whole. And this right here is why choosing the right tool is absolutely critical. That technical jargon you see O of n squared is just a mathematical way of saying that for bubble sort, the workload absolutely explodes as the list gets bigger. If you double the number of items, you basically quadruple the work. But look at merge sort. Its complexity, O of n log n, means it scales so much more gracefully. As the amount of data grows, the effort required grows way, way slower. For a large data set, this is literally the difference between getting a result in milliseconds versus waiting for hours. All right, third drawer in our toolbox, tools for finding paths. Now let's circle all the way back to our original question about your GPS, because finding the fastest route requires a very specific set of tools. The ones designed for, you guessed it, finding paths. So to find a path, you first need a map. And in the world of programming, this map is a data structure called a graph. It's actually pretty simple. It's just a collection of points, which we call vertices, and the connections between them, which we call edges. A city map is a perfect example of a graph. Intersections are the vertices and the streets are the edges. Or think of a social network, where people are the vertices and their friendships are the edges connecting them. And the recipe for finding the shortest path on that map is a famous one called Dijkstra's algorithm. And you know what? It has this beautifully simple starting point. It basically begins by assuming that the distance from where you are to every other point on the map is infinite. It starts off knowing absolutely nothing. And then, step by step, it starts exploring the graph. It checks the neighbors of your current location, it updates their distances if it finds a shorter path, and it always moves to the closest unvisited point. By methodically expanding outwards from where you started, it guarantees it will find the absolute shortest path to every single destination. And that, my friends, is the engine humming away inside your GPS. What's really cool is that these pathfinding and analysis tools are used in some truly surprising places. I mean, the same exact logic can be used in computer vision to find the brightest areas in an image, or in genomic sequence analysis to identify important segments of DNA, and even to detect when a computer program gets stuck in an infinite loop. It's just a remarkably versatile tool to have. And this all comes down to the final section, the art of problem solving. Because, having a toolbox is one thing. Being a master craftsman or a really great programmer is all about knowing which tool to use and when to use it. And here's the crucial point. Even for something like finding the shortest path, there is no single best tool. Dijkstra's is super fast, but it completely fails if a path has a negative cost. I mean, you can't have a road with negative distance, right? The Bellman-Ford algorithm, on the other hand, is slower, but it can handle those negative values. Now, why would you ever need that? Well, think about analyzing currency trades, where converting from one currency to another and back again might actually earn you money. That's a negative cost. So for a roadmap, you use Dijkstra's. For finding arbitrage opportunities in finance, Bellman-Ford is the only tool for the job. And that's really the big takeaway here. The magic of software isn't about memorizing thousands of lines of code. It's about understanding the problem you're trying to solve, knowing what tools are available in your toolbox, and having the wisdom to select the right one based on its strengths, its weaknesses, and all those trade-offs we've been talking about. At the end of the day, this is the art and science of problem solving, and it's a field that's always evolving, where today's impossible problem is just waiting for someone, somewhere, to invent a brand new tool for the toolbox. So the final question is, what's that next great challenge going to be? Thanks for watching.